If we look at this problem from the last video, we might notice that it took quite a few tries before we found a divisor that worked out. Sometimes with Jefferson's method problems, it can take a really long time to find the right divisor if we rely on guess and check. In this video, we're going to look at a method that will help you find a divisor that will work a little bit more quickly than relying on guess and check will. Note that this technique is optional. You don't have to use the technique I'm going to show you on exams, but if you prefer it to guess and check, you're welcome to use it. Now we're going to talk about threshold divisors. A threshold divisor is a divisor that will cause a state to get n seats when the state's corresponding modified quota is rounded using the apportionment method specified rule. When using Jefferson's method, we can find threshold divisors for each state by dividing the state population by the number of seats we want the state to get. So let's look at an example. Let's suppose state A has a population of 5,342 and is due 10 seats in its initial allocation. Jefferson's method is being used. What modified divisor will guarantee state A gets a quota of 11? If we remember, the rule for Jefferson's method is rounding down. If their quota is exactly 11, they're going to be allocated 11 seats. And we want them to get more seats because in Jefferson's method, you always start out by allocating too few seats. So if we were to take 5,342 and divide it by 11, we end up getting 485.6363, ... but we'll just round it off to 4 decimal places. So now if we take our population of 5,342 and divide it by this number over here, let's see what potential quota we could end up getting. 11.000, but if this is our modified quota, when we round everything down, this state would end up being due 11 seats. Which is generally what we want to have happen with Jefferson's method. We want to be giving out more seats. The general technique for finding threshold divisors in Jefferson's method is to take whatever the state population is and divide it by the number of seats you would like to see that state get. Now let's look at this example again that we had in the last Jefferson's method video. So just remember, our house size here was 37. We had our natural quota here. We had our initial allocation, which was too small. These would be our threshold divisors for Jefferson's method. In each case, we look at the state population and divide it by the number of seats we would like it to get. Originally, Cumberland got 9 seats, and because we want to give out more seats, because we still have 2 more seats to give out, we divide by 10. So that tells us if we use 2,545 as our divisor, Cumberland's going to end up getting exactly 10 seats. But that doesn't tell us anything about how many seats the other states are going to end up getting. Because remember, we don't want to give out too many seats. And we can go through and do this for all of the other states, and then we'll figure out which one we want to try. Hancock state population, 9,549 divided by 4, because originally they got 3 seats. Tells us if we use 2,387.25 as a divisor exactly, they're going to be due exactly 4 seats. And we would do the same thing for the other ones. Lincoln originally got 11 seats, so we would divide their state population by 12. Washington got 1 seat originally, so we divide their state population by 2. York got 11 seats originally, so we divide their state population by 12. Our natural divisor was 2,609.1892, and we need to give out 2 more seats. Generally, what we could do is look to see which threshold divisors are closest to the natural divisor. Remember, if we make the natural divisor a little bit smaller, maybe this will go from 35 to 36, but we want it to go to 37. Now, since we need to allocate 2 more seats, trying a modified divisor a little bit smaller than the threshold divisor that is second closest to the natural divisor is a good place to start. If we needed 1 more seat, we'd have tried the first closest. If we needed 3 more seats, we'd have tried the third closest. If we look at our natural divisor, which is 2,609 point stuff, the first closest threshold divisor we have is for Cumberland. So that tells us if we use a divisor of 2,545, Cumberland's definitely going to get 10 seats. Now, if you remember from when we worked through this problem before, this divisor wasn't small enough because we had a divisor that was smaller than this that worked out. Our second closest divisor is 2,000 496.8333, which is a lot closer to the divisor we had that worked. If you remember from the last video, I believe it was 2,450 was the divisor we had that worked. Now this is a little bit bigger than that. If we go smaller, it can work, but if we were to get as small as 2,401, then York would end up getting an extra seat and it would be too small. So if you want to use threshold divisors to help you avoid guess and check and get a divisor that will work more quickly, this is a technique you could use. You would find the threshold divisors for all of these states, and then depending on how many more seats you need to allocate, you would go for the first closest threshold divisor or the second closest or the third closest, and so on. When using threshold divisors to help find a modified divisor, if you need to allocate m more seats, start with a divisor near the threshold divisor mth closest to the natural divisor. But this isn't guaranteed to work in every problem. Lots of times it does, but every now and then it doesn't work. You can still use these divisors as a good place to figure out where you should be guessing, because sometimes it can be hard to figure out what you should be doing with guess and check. So now to talk about situations where this threshold divisor technique isn't always reliable, we need to talk about the quota property. The quota property says the number of seats a state is allocated is equal to the state's natural quota, rounded either up or down. What this means is a state shouldn't end up getting more than one extra seat in their final allocation. Okay, for example, if the quota property is satisfied and a state's natural quota is 13.4567, they can only end up getting 13 or 14 seats in the final allocation. If they end up getting 15 seats or more seats, the quota property would be violated. So here's an example where Jefferson's method violates the quota property. Suppose Consumer Reports wants to test 150 cars based on the percentage of each car on the market. How many of each car will they test if they use Jefferson's method? So we have different types of cars here. We have the percent on the market. So you could think of this as being like population or state population. We have our total population or percent, which would be 100. Our natural divisor would be total population divided by our house size. House size in this case is 150 because it's the number of things we want to test in this case, or the number of what we would be giving out. So we do that division, we find our natural divisor. Then we use our natural divisor to get our natural quotas, and we have our initial allocation, which is too small. It adds up to 147, we need to allocate 3 more. So now for these modified quotas, to figure out where they came from, we'll look at the threshold divisors that we found for this. Remember, this was our natural divisor, 0.6667. We find all of our threshold divisors by taking each state population and dividing it by the number of seats we want them to get. Originally, Ford got 24, so we're dividing by 25 because we want them to go up. GM originally got 28, so we're dividing by 29 because we want them to go up. So we needed to allocate 3 more seats, so we will look for the third closest threshold divisor to the natural divisor. So our first closest is over here. Our second closest would be Ford, and our third closest would be Honda. So this is first closest, second closest, third closest. So if we try 0.6531 or something a little bit smaller than that, as long as we don't get smaller than 0.6526, we would hope it would work. So we'll go back to that now. If we try 0.653, which is a little bit smaller than the third closest threshold divisor, these are the modified quotas we get. And if we round everything down, we get 25, 28, 16, 22, and 60. This all adds up to 151, which means our modified divisor is too small because our allocation here is too large. So now we would want to try to make our divisor a little bit bigger because it was too small here. So if we make it just a little bit bigger, 0.654, we'll end up getting something that works. So we round everything down to see what our new allocation is. And this adds up to 150, which works out. And now we want to figure out, well, why is that the case? If we look at the threshold divisor other would need to get 60 seats, which is 2 more than they were initially allocated, it ends up being 0.654, which if we compare to what we thought was the third closest, this is the actual third closest threshold divisor. So when we divide by 0.654, which is a little bit smaller than this, everything ends up working out over here. And other, which was originally allocated 58 seats, ended up getting 60 seats. So the quota property is violated here, and this is just an example of how threshold divisors don't always work out. However, in a lot of problems they do work out. They can make your life easier, but if you thought this video was really confusing and you want to focus your efforts on just understanding how to do Jefferson's method in general and rely on guess and check, that's fine. You don't have to use this if you don't want to, but if you like it and you think it's easier, feel free to use it.